Today, I'll go through quickly the Advanced Fuels Campaign, its major goals and activities, so that hopefully you can design proposals to these 2 and 3 areas that we're calling for this year, such that they'll have high relevance and high technical value. Our campaign is really split into 3 pieces. We have a portion that is responsible for developing advanced light water reactor fuels with enhanced performance, safety, and reduced waste generation. We commonly refer to this as the accident tolerant fuel area. That is our primary goal at this time, and I'll say a little bit more about that in a little bit. A second piece, and really a different fuel development program, is the transportation fuel program. We're responsible to investigate, perform R&D in transportation fuels to give the department options for the future for dealing with resource utilization and nuclear energy, as well as destruction of the minor actinides and reduced waste generation. Our program has existed for quite a while, and we have been proponents of developing and facilitating the development of capabilities for studying advanced nuclear fuels and improving the techniques and ability of learning about the fuels under irradiation. And so for that regard, we have sort of a cross-cutting area that we call the Capabilities Development for Science-Based Approach. And this area focuses on advanced characterization and PIE, post-radiation examination technique development, advanced in-pile instrumentation development, separate effects testing, transient testing infrastructure. And we'll talk a little bit more about that today. I have a slide on that. We've put in calls and focused our calls down to very specific things over the years, and sometimes specifically in 1 or 2 of these specific areas in capabilities development. Last year we specifically asked for techniques coupled with modeling simulation capabilities. And you can see that is our connection to the NEAMS program over in another portion of NE that is responsible for developing multi-scale, multi-physics fuel performance codes and modeling simulation tools. And so you'll see us put a link in our call for work and activities, experiments usually that are easily connected to the multi-scale, multi-physics modeling activities. Our high-level technical objectives are documented and come from a high-level document that is the Nuclear Energy Research and Development Roadmap. It was originally written in April of 2010 and issued in April of 2010. You can actually access this document for background information on the DOE website. I provide the link to that website or that document here at the bottom, so you can have that for your reference. But basically, we're tasked with identifying, selecting the advanced light water reactor fuel concepts. We have a specific goal of demonstrating a lead test rod in the next 5 to 7 years, specifically by 2022. We need to complete design, conceptual design for baseline transportation fuel technologies in the coming years, as well as identify and demonstrate feasibility of innovative concepts that provide considerable advantage compared to baseline technologies. We refer to this area as our grand challenge area, but drive some innovative activities in our primary fuel research areas. We'd like to be able to achieve state-of-the-art R&D infrastructure that can be used to transition from, say, an empirical-based approach to the development of advanced nuclear fuels and materials to more of a science-based approach. I would say that we do this by trying to build experiment coupled with modeling simulation into much of our program, as well as fundamentally developing and understanding the behavior of fuels and materials at the microstructural level. And then, of course, our connection to the NEAMS modeling simulation area is supporting the development of a predictive multi-scale, multi-physics fuel performance code. So moving to the accident-tolerant fuel area, so I'll give this background of our major fuel development activities so that you'll know what is, or have some idea what is of primary relevance to the program. Fuels with enhanced accident tolerance are those that, in comparison with standard UO2 zircaloy system, can tolerate loss of active cooling for a considerably longer period of time than the existing system. We also refer to this as just providing a longer grace time for the reactor operator to respond to off-normal events. You can see some of the attributes that we are currently targeting for improvement and what we would assume and consider as enhanced accident-tolerant performance. Near-term goals for the accident-tolerant fuel program, we are currently utilizing the infrastructure at across the national laboratories as well as the universities to support the fabrication, irradiation, and testing of accident-tolerant fuel concepts. You'll see in some of the background slides that we have a number of universities working through the NEUP program as well as through direct IRPs with specific accident-tolerant fuel concepts. Those universities and entities are actively participating in the campaign, and the goals of the campaign to demonstrate technologies by 2022. We are currently in the final pieces of initiating the first irradiation of an accident-tolerant fuel experiment in the advanced test reactor here at the Idaho National Laboratory. That experiment will start next month. It goes into the reactor within the next month, and will go through the next 2 to 3 years, basically testing some of the accident-tolerant fuel concepts that the campaign is currently working on. We're initiating the test planning and preliminary design of loop testing capability for an accident-tolerant fuel test in the advanced test reactor. This is needed for cladding coolant interaction. A primary test of accident-tolerant fuel concepts will be the cladding and coolant interaction. And then a major activity for the department, recently it was decided by the Department of Energy to refurbish and restart TREAT, which is a transient testing experiment capability at the Idaho National Laboratory. And the Advanced Fuels campaign will support the development of transient test loops for accident-tolerant fuels as well as long-term transmutation fuel testing. We currently have some major activities funded in the accident-tolerant fuel area directly with industry. All 3 major vendors, Areva, Westinghouse, and General Electric, are all individually leading a FOA effort. These are multi-entity teams that are coordinated between industry and universities to develop a accident-tolerant fuel concept. They're all 3 working in different areas, and each of those 3 will be included in the upcoming experiment that we put into the advanced test reactor. This slide actually says that we need a second allotment of funding in early 2015. Those FOAs, it's been announced, have been refunded. Moving to long-term transmutation fuel, the motivation behind investigating transmutation fuel development is in the actinide management in fast reactors. Over in the advanced reactor area of DOE, there's an active program to develop the next fast reactor technology, and we're tasked with providing the fuel options for that fast reactor, which drives us to investigate what we refer to as recycled fuel for fast reactors. In this case, because of budget constraints, we focused our efforts on the metallic fuel system for fast reactors and incorporation of the minor actinides, americium, neptunium, and possibly curium in the future, as well as plutonium for resource extension. That metallic fuel point of contact for more information is actually Steve Hayes at the Idaho National Laboratory. He's the technical lead for transmutation fuels. The program is primarily focused on research and development, supporting a 2050 demonstration of full recycle at the engineering scale. And so we're currently working on advanced casting and fabrication techniques, characterization of material properties of minor actinide-bearing fuel compositions, and then the irradiation behavior of those fuel compositions in pile. And then developing advanced claddings having high burnup capability. Many of you have probably seen some of our calls in the past where we've asked for high dose, high DPA capable cladding materials, and the program is still working towards those types of goals. In the cross-cutting area, in general, we have 4 primary areas. Looking at initiating prototypic testing of advanced in-situ and advanced in-pile measurement techniques. We've long advocated for understanding the microstructural behavior of fuels under irradiation. And so instrumentation and capabilities that get us closer to that end have been an interest in the past. Continued development of advanced characterization techniques, including hot cell mock-up of multi-sensor apparatuses. The IMCL is a new facility that is at the Idaho National Laboratory. It's the Irradiated Material Characterization Laboratory. It will house high-resolution microscopy equipment, and so to that end, we have asked for, in the past, advanced microstructural experimentation techniques coupled with modeling simulation that will get us towards instrumentation and capabilities that can be used on irradiated materials. There were a couple of NEUPs that were funded in 2013 in this area, so those have been of interest in the past. The Bison code is the actual name for the NEAMS tool that is currently used for fuel performance modeling. And so developing experiment modeling and simulation capability coupled with the NEAMS tools is of interest to the program. Currently this year, within the program, within the Advanced Fuel Campaign, we were expanding the use of this tool to look at some of the accident-tolerant fuel concepts, and we can talk about that. I'll talk about that a little bit more when we get to the actual call slide. And then we have an activity that is more in the laboratory system that is obtaining americium neptunium feedstocks for use in domestic energy programs for our advanced fuel program. So specifically on the calls for this year and the 2014 NEUP call in FC-2.1 and 2.2, I provide the language that Dr. Goldner and I have drafted for this year. We were asking for, in FC-2.1, advanced fabrication techniques that are applicable to fuel and core-related systems of interest to our program, meaning the accident-tolerant fuel program for light water reactors and the transmutation fuel program for fast spectrum reactors. We're looking for novel fabrication techniques, and I note novel fabrication because we've investigated over the years different techniques for fabrication, specifically related to transmutation fuels, specifically things that can be easily remotized as opposed to some of the more traditional methods for fabricating advanced fuels. For instance, in the past, we've investigated spark plasma sintering, microwave sintering, advanced casting techniques. Even we had a project a couple of years ago that was funded in the program to look at freeze casting techniques for fuel fabrication. So we would be interested in entertaining some novel fabrication techniques as long as they're applicable to our primary fuel development programs. We're also interested in advanced fabrication techniques for core structural materials, and so we'd be interested in seeing those in FC-2.1 this year. Under the FC-2.2, it's a little bit different. Sometimes we call for specific cladding development in FC-2.2, but this year we are asking for advanced characterization techniques to enhance the ability to link integral experimental data with microstructural level material property behavior data or models. Specifically, we'd like these advanced characterization techniques to be connectable to the NEAMS fuel performance tools that the NEAMS program has developed. And specifically, technologies that will be low relevance in this call would be thorium-based fuel technologies as well as molten salt-based technologies. And not that those things aren't of interest in the research community, it's just for our program, those are very low relevance activities. We have a new integrated research project that we would like to call for this year, FC-1, Integrated Research Project on Evaluation of Fuels and Systems with Enhanced Accident Tolerance. One of the things we'd like to be able to do is estimate the time to melt for fuel and core components. We'd like this capability to be, and computational tools to be commensurate with the DOE NEAM program tools. We'd like to have proposals that propose to analyze the key areas of cladding and core component performance, thermomechanical fuel performance, steady state and transient neutronics, thermohydraulics, but most importantly, the tool must be able to provide an estimate of the time to melt for the core components. And we strongly encourage the coordination and use of the DOE and E4 NEAMS program tools. Some documents that might be of interest to the community for background and to see what is actually being funded within the laboratory system. One of the deficiencies I've seen in past proposals has been proposing to do work that is already funded within the laboratory system and is sort of duplicative of the laboratory system work. So we'd like maybe think about getting more information out to the community so that they can identify the work that is already ongoing in the laboratories and then propose activities and work that would be beneficial and commensurate with the activities already funded in the laboratories. This document that's listed here is the 2013 Accomplishments Report for the Advanced Fuel Campaign. It actually has a number of contact names at different national laboratories as well as universities that you can use and contact for information on their work and the work that they've completed for the Advanced Fuels Campaign. There's an overview of the accident-tolerant fuel program that's available on OSCE. And then also there's a recently published accident-tolerant fuel performance metrics document that talks about how we plan to evaluate the attributes and metrics of candidate accident-tolerant fuel concepts. That's what I have for now. You can get more information either directly from myself, John Carmack at inl.gov, or from Dr. Goldner at frankgoldner.goldner@nuclearenergy.gov. I strongly encourage you to review the previous fuel-related awards on the NEUP website. You don't want to propose a project that is currently funded under NEUP because that will be low relevance. I think I can take questions now. I have a number of slides for your information for background. And so if you have any questions on those, we can take those now, or you can email me or Dr. Goldner.
We'll take questions over the next few minutes. Can you explain what you expect from the IRP?
So one of the things that we've been looking for, people have built models, have built tools using the Moose Bison environment, which is the NEAMS program tool used for fuel performance. That tool currently, those efforts have primarily looked at the steady state performance of accident-tolerant fuel concepts. But there are models that are needed to be put into the NEAMS tools, as well as capability to go from steady state analysis to estimate of melt. We're not asking for post-melt because that's a much more complicated endeavor, and I think there are capabilities in the university community that can help us with models and a modeling infrastructure using the NEAMS tool that can go from include the steady state analysis, but get us an estimate of time to melt. Which we're interested in the time to melt specifically because that will give us a metric that we can use to assess some of these accident-tolerant fuel concepts.
Next question. Is this program considering accelerators for transmutation?
Not at this time. This program has considered accelerator transmutation of waste years ago, back in the early 2000s, but that is not a current activity in the Department of Energy in this program.
Next question is that you mentioned metallic fuels. Are ceramic fuels also entertained?
Yes. We have, over the past couple of years, we have greatly sort of defunded our activities in ceramic fuels for fast reactors. But we have some international collaborations that have considered and have access to data on ceramic fuel compositions for transmutation. I would say they would be a medium to low relevance. It depends on what is actually proposed by the community. And I would say send me a note, or give me a phone call to discuss what is actually being proposed. The difficulty for us with ceramic fuels is we have investigated, say, nitride fuel system in the past as an advanced fuel in the ceramic system, and had a lot of trouble incorporating the minor actinides in the nitride fuel system. And so we have that information available to us, and that really drives us to actually choosing the metallic fuel system, because it would be very difficult for us to envision fabricating actinide-bearing nitride fuel reliably. So I would say be careful about what you propose in the ceramic fuel area to me. It would probably want to check that with me first.
Okay, the next question is, how would we get access to TREAT? Should we have an INO researcher on the proposal that has access to TREAT, or is there another option?
So there's no access to TREAT at this time, because TREAT is currently scheduled to be brought back to operation in 2018. In our program today, what's going on is more the development, design, and construction of the test loops that would be used for transient testing and TREAT. Send me an email with your contact information, and I will put you in touch with Dr. Dan Wachs, who is the scientific coordinator here at INL for TREAT transient testing. He would be very interested in speaking with people in the university community with capabilities in understanding transients, understanding what we need to do with transients in the future, or even proposing experiments in the future using the TREAT transient test system. So I will put you into contact with our specific scientific coordinator to facilitate better proposals and more connected proposals.
Moving on to the next question, what is the funding level of IRP-FC-1?
It hasn't been determined yet. I would say typically in the past, IRPs have been funded at the $1 million level per year.
And that's $1 million per year, meaning $3 million project over the lifetime. The next question, which I'll answer, John, is it says, since we don't have the FOA, the fuel cycle or FC category is only open to universities as LEAD. So that is considered if you look back to the first presentation, it's a program supporting area, and the IRP is a program directed area, both only applicable to university leads with national laboratory and industry collaborators. John, the next question in regards to the IRP. Time to melting greatly depends on accident, scenario, and transient thermal hydraulics, ECCS, etc. Do you expect the IRP to develop such capability?
Or use the tools that NEAMS is developing for that purpose.
Next question regarding FC-2.2. Can you please restate the goals of the advanced characterization section?
So we've the goal is to one of the powers of the NEAMS fuel performance tool that's been developed is being able to model very fine microstructural behavior in fuels. And so we're looking for advanced characterization techniques that can provide us with data to supply those models. And then if possible, even develop the model to be put into the fuel performance tool, but not necessarily have to develop the model. So in the past, for instance, we funded an NEUP last year with Dr. Peter Hoseman at UC Berkeley to look at advanced uses of the FIB technology to investigate micromechanical properties of irradiated fuels, and understanding how to use that technique with irradiated fuel material. So that type of advanced characterization, I think, is what we're after with FC-2.2. But we're open to proposals because we don't pretend to be the experts in advanced materials characterization technique development. Much of that activity has taken place in other material, non-radioactive material systems over the years. We believe there are characterization techniques that have been developed for other material systems that we could possibly apply to irradiated fuels in the future, even if that may include additional development on our part in the laboratory system to handle those materials. What we've seen in the program is using FIB-type technology to prepare samples that can be used on advanced characterization tools. But how to use those tools with irradiated fuels is of interest to us.
Thanks, John. Next question is, what about TRISO fuel type in different form for fast reactors?
So I'm not sure, maybe somebody in the NEUP office can tell me, can let us know if there's a specific call for TRISO fuel for high temperature gas reactors. I think that may be in a separate call. What we do have in our program is the use of a TRISO particle in a ceramic matrix, not graphite matrix, but for control or containment of the fission products for advanced accident-tolerant fuel. But it's not strictly the TRISO fuel concept for high-temperature gas reactors. So that distinction has to be made because our program does not fund the TRISO fuel work for the advanced gas reactor.
And to answer your question, John, this is the only work scope area that deals with fuels. We have a separate area that's called MS-NEAT-1 that is new this year that you can submit other ideas to that may not fit underneath the umbrella of any of these programs. And that's not just for this question, but as an overall comment as we made this morning, that if there's something that doesn't quite fit.
That may be also, something for thorium or molten salt technologies that our call isn't really relevant to. There may be a blue sky type call that is more amenable to fuel technology, those types of technology.
Exactly. Now, to clarify the additive manufacturing, that's referring to 3D printing.
So you need to refer to some of the past proposals. I think, and I'll direct you to, there may be an SBIR that's also relevant to, because I think we have an SBIR that's recently been funded in 3D printing. And so I would send me your contact information for that before you make that proposal, and I will put you in contact with the person who is in charge of the SBIR activity. And so we would encourage communication so there's no duplication.
And to reiterate what was stated before, that would be a more appropriate proposal for NEAT-1, which is advanced manufacturing.